Hello, y'all. Welcome to lesson 107 of my DP chemistry curriculum. Today we're doing reactivity 3.2.1 and 2. In the first section, we're going to talk about oxidation and reduction, which is described in terms of electron transfer, change in oxidation state, oxygen gain or loss, or hydrogen gain or loss. Then we're going to deduce oxidation states of atoms in a compound or ion, which we have done before, and we will identify the oxidized and reduced species in a chemical reaction, as well as the oxidizing and reducing agents in that reaction. We will then move on to 3.2.2, where we'll talk about half equations, separating the processes of oxidation and reduction, showing the loss or gain of electrons, therefore showing that we will likely be working with the terms of electron transfer for oxidation and reduction. Using that, we'll deduce redox half equations and equations in acidic and neutral solutions. We will not be moving on to basic solutions. So starting off with this section, what is redox? Well, redox is just joining the words reduction and oxidation. But now the problem is, what is reduction and what is oxidation? So to define these terms, let's start at a common example of a redox reaction. And one of the most common redox reactions that most people are familiar with is the rusting of iron. Iron solid, when reacting with oxygen gas in the air, reacts to form what we know as rust, which is Fe2O3. And we'll go ahead and balance this equation out. We have 4 irons, 3 oxygens, 4, 2 rust. So this is a standard redox reaction. Now, we mentioned many times we're going to be looking at oxidation states. So let's start by looking at the oxidation states of these elements. As a quick reminder, back in lesson 62, we defined our oxidation states, which I'll start using OS just to shorten things, as a assigned number uh, to an element representing or showing the number of electrons lost or gained. And they don't have to be fully lost or gained, they can be partially lost or gained. But using that definition, we'll go ahead and just look at our equation down here. Iron in the original problem starts out with an oxidation state of 0. It's elemental iron. It hasn't gained or lost any electrons. Same with oxygen. Elements on their own have a neutral or 0 oxidation state. So when we identify those oxidation states, they both start as 0 in their elemental form. Now here, iron is representing the 3 plus cation. So it has a plus 3 oxidation state, while oxygen is representing the 2 minus anion, so it has a minus 2 oxidation state. And so as we look at these oxidation states, we can notice two things. Iron lost electrons, or the oxidation state increase oxidation state. On the other hand, oxygen gained electrons, or decrease oxidation state. And so what actually happened in this reaction? Well, we can see that when oxygen is added to iron, we actually say that the iron oxidizes, which makes sense. When you add oxygen to something, it will oxidize. That's where the word comes from. Furthermore, if one species oxidizes, the other reduces. So now we have our two terms, oxidize and reduce, or oxidation and reduction. In this case, our other species is actually oxygen itself. Iron is one reactant, oxygen is the other reactant. So here our iron oxidizes and our oxygen reduces. We can take a look at another very common redox reaction. This one would be photosynthesis. Now in photosynthesis, we have 6 carbon dioxides plus 6 waters. I'm going to ignore state symbols for the time being. Turn into glucose, C6H12O6, plus 6 oxygens. Now, we're going to look at individual oxidation states here. Carbon has an oxidation state of +4. Oxygen has an oxidation state of -2. Hydrogen has an oxidation state of +1. Oxygen has an oxidation state of -2. If you still have trouble with oxidation states, I highly suggest you go back to lesson 62 or video 62 and you relearn how to calculate these. Now, with glucose, carbon has an oxidation state of 0. It's not in its elemental form, but it's 0 because hydrogen is +1, oxygen is -2, and those will cancel out, meaning carbon must be 0. And oxygen, now back in its elemental form, is 0. So what we notice is that hydrogen doesn't undergo any change. So no change for hydrogen. Nothing's really happening. Carbon goes from a 4 to a 0. So what we notice here is carbon, well, actually I'll hit both of them, and oxygen in water is going from a -2 to a 0. So when carbon turns into glucose, it is gaining hydrogen. And oxygen in water is losing hydrogen. So what we actually end up seeing is that carbon gains hydrogen. We call this reduction. And oxygen loses hydrogen and is oxidized. Now that's odd because oxygen is now being oxidized, not being reduced. Nothing is really gaining oxygen, so we can't really refer to the gain of oxygen. However, things are gaining or losing hydrogen, and we can refer to that. You'll notice once again, the oxidation state goes from +4 to 0. It's reducing. Meanwhile, the oxidation state in oxygen is going from -2 to 0. It's oxidizing. So it is increasing in oxidation state. Now, the last example I'm going to use to kind of demonstrate oxidation and reduction is just a common reaction between two metals. So generally we can see the reaction between zinc and copper sulfate or copper 2 sulfate, cupric sulfate. So we take our zinc solid, we react it with aqueous copper sulfate, and in solution when they react, we will get zinc sulfate, now aqueous, plus copper solid. When looking at oxidation states, once again, our elements are going to be 0. We know that sulfate has a 2- charge, therefore copper must be +2, and zinc also must be +2 when bonded to sulfate. So what we realize is zinc increases in oxidation state, copper decreases in oxidation state. What's happening is we're seeing a transfer of electrons. Zinc loses electrons. It is oxidizing. Copper gains electrons. It is reducing. So now when we combine these three different types of oxidation or reduction, we can kind of create four main definitions. So we're going to do that in a chart. So first, and honestly the easiest one, the one that appears in all of them, is we can look at oxidation states. If the oxidation in state increases, well, it's being oxidized. If the oxidation state decreases, it's being reduced. Literally, the oxidation state is reducing or decreasing, and therefore it is being reduced. To me, this is the most straightforward way to find whether something is being oxidized or reduced. Even in all three problems, I tracked oxidation states to really make sure that oxidation or reduction was happening. So oxidation state is kind of your go-to. Now, in addition to oxidation state, we're going to often be looking at electron transfer because electron transfer is directly related to oxidation state, as that's where we kind of pull oxidation states from. If we are losing electrons, then we oxidize. If we gain electrons, we decrease our oxidation state and reduce. The last two are kind of older definitions where the word oxidize comes from. If we're looking at oxygen transfer, if we gain oxygen, we oxidize. If we lose oxygen, we reduce. Or with hydrogen, the exact inverse. If we lose hydrogen, we oxidize. And if we gain hydrogen, we reduce. Now, once again, I will repeat that we will most often use these definitions right here. And so I'm going to kind of focus on that for the remainder of the lesson. So I'll just highlight these. Now, what was the other part of oxidizing and reducing agents? Well, how do we incorporate these terms? We've learned oxidation, we've learned reduction, but now what are agents? So oxidizing and reducing agents. Well, an agent is something that causes something, so causes something. You may have heard someone referred to as an agent of chaos. They're spreading chaotic energy, or an agent of good, or an agent of evil. An agent is something that causes something. So an oxidizing or reducing agent is the thing that causes oxidation or causes reduction. So oxidizing agent that causes oxidation, which therefore means it is reduced itself. So when we go ahead and look at something like, let's go back to our rust. When we look at rust, iron is oxidizing. The thing causing it to oxidize is oxygen. Therefore, oxygen is the oxidizing agent, and it itself is reduced. These terms, oxidizing and reducing agents, are probably the most problematic because they cause more kind of like confusion and chaos as they are using the same words but mean the opposite. So a reducing agent causes reduction and is oxidized itself. So back in that first example, iron is a reducing agent. It is oxidized, but it is causing oxygen to be reduced. So these are just terms that we need to be able to be fluid with, and we need to be able to use them to refer to many different species within a reaction. If the terminology is confusing, I strongly suggest you try some practice problems, work through it, and continue to use oxidizing agent, reducing agent, oxidation, and reduction all simultaneously as you go through redox problems. All right. So now that we have the terminology out of the way, which is mostly 3.2.1, moving on to 3.2.2, let's now look at actual redox reactions, how to write and balance them. So for a redox reaction, what we really want to do is to properly represent both oxidation, and reduction. So to do this, we use what are called half reactions. A half reaction is simply uh, a reaction showing either oxidation or reduction. And furthermore, we represent transfer of electrons. So we're going to bring those electrons back. So when we look at half reactions, we'll take some of the examples we've seen before, starting with something simple like our copper sulfate reaction, or our zinc and copper sulfate. So in the original reaction, I'm just going to go ahead and copy it. Oops. We have our zinc reacting with copper sulfate to produce zinc sulfate and copper. Now, in solution, copper sulfate actually separates into copper aqueous 2 plus and sulfate aqueous 2 minus. Furthermore, zinc will do the same thing. So we get zinc aqueous 2 plus and sulfate aqueous 2 minus. These are ionic compounds, they'll break down. Now, because of this, we have sulfate on both sides, and we can actually just cancel it from our equation. So we can represent this reaction as zinc solid plus copper 2 plus aqueous reacts to form zinc 2 plus aqueous plus copper solid. This is now a much easier reaction to handle. Now we're going to use this idea of half reactions. So we have our oxidation half reaction. And the oxidation half reaction will show zinc solid becoming zinc 2 plus aqueous. However, we mentioned we also show transfer of electrons, so we also have 2 electrons. Those are removed from the zinc, so we have to show that. In our reduction half reaction, we have copper 2 plus aqueous plus 2 electrons, and that will react to form copper solid. Once again, we're showing the transfer of electrons. We have defined our oxidation reaction as the one with zinc and the reduction reaction as the one with copper. These are our half reactions. Well, if we want to figure out our full reaction as well, we just have to add them together. So to get the full reaction, I can just add them. The electrons will cancel out. So if I move the electrons to the side so I can remove them later, zinc plus Cu2 plus reacts to form Zn2 plus Cu plus 2 electrons. And I'm going to add in those state symbols. We then see that 2 electrons on the reactants and 2 electrons on the products cancel out. And we once again have our redox reaction. So these are half reactions, and these are how we can actually use our half reactions to go back into our real reaction. However, there are some where these are simple with, but there are others where we now have to do a little bit extra work. And this is where half reactions become a bit more handy. Let's return back to our reaction of rust. We know for rust that we have 4 iron plus 3 oxygen reacts to form 2 Fe2O3, 2 iron 3 oxide. Now, our oxidation reaction is simply iron reacts to form iron, and it has a 3 plus charge plus 3 electrons. Oxygen in our reduction reaction becomes O2, reacts to form 2O, 2 minus, whoops, I am missing are 2 electrons. Or, sorry, not 2 electrons, 4 electrons, because we have 2 minus charges. Now, if I combine these two reactions, I unfortunately will still have electrons in my reaction. So when I add them up, I get Fe plus O2 plus 4 electrons reacts to form Fe3 plus O2, oops, O2 minus, 2O2 minus, plus 3 electrons. I can cancel out 3 electrons from the right side, but I still have 1 electron on the left. Electrons are not allowed in chemical reactions. They're allowed in our half reactions, but not in real chemical reactions. So we actually have to modify our equations. We have to do a little bit of, honestly, algebra to get this working. So we'll do take two. We will balance half reactions with each other. And the main focus is actually our electrons. We want to get those electrons out. So to balance 3 electrons with 4 electrons, or 3 with our 4, I will multiply this whole thing by 4. Similarly, I'll multiply our reduction by 3. So my new reaction stands 4 iron reacts to form 4Fe3 plus 12 electrons. My reduction reaction now becomes 3O2 plus, whoops, not 4, 12 electrons to form 6O2 minus. Now when I combine these, so I sum them together, I get 4Fe plus 3O2 plus 12 electrons reacts to form 12 electrons plus Fe2Fe2O3. I'm still maintaining that I have 4 iron, 2 Fe2, and 6 oxygen, 2O3. I've just combined them. When I do this, I notice my electrons fully cancel out, and my reaction is quite simply as follows. 4Fe plus 3O2 react to form 2Fe2O3. And just like that, we have our starting rust reaction. Everything is balanced. So we use half reactions to help us balance this out. Balancing half reactions is something that takes a lot of practice, and you will do it more within the chemistry classroom. Now, both of these reactions we saw happen in neutral conditions. However, many redox occur in acidic conditions. So in an acidic condition, we can add during half reactions two reagents. We can add water and protons. The reason we can do this is because protons are free in acidic conditions. They're just floating around. That's what makes it acidic. And water is the solvent for which all these reactions are taking place. So you can always add these to help you in half reactions. So why do we even need that? Well, let's do one final example for today. And this will be an example of an acidic condition. So we're going to look at Fe2 plus dichromate Cr2O7 2 minus reacts to form Fe3 plus chromium 3 plus ion. And we're going to say this is, once again, acidic conditions. So the first thing we need to do is identify our half reactions, our oxidation and reduction half reactions. To do that, we need our oxidation states. Well, iron 2 plus clearly has an oxidation state of 2. Iron 3 plus clearly has an oxidation state of plus 3. I can infer already that this is oxidation. Therefore, I'll infer that my chromium is reduction. If I want to actually do the math, I see that 7O2s is a minus 14. There is a 2 minus charge on this as well. So we only have to balance minus 12, meaning that each of these is going to be 6 plus. To just showing you that math, if two chromiums are 6 plus, together that's going to be 12 plus. 12 plus and 14 minus is 2 minus, which is the overall charge. Again, if oxidation states are making it difficult, please go back to lesson 62 and check your oxidation state math and practice it some more. It is invaluable in redox reactions. All right, moving forward with our oxidation half reaction, Fe2 plus reacts to form Fe3 plus, and we're going to add 1 electron. Easy enough. We have fully balanced our oxidation half reaction. This, however, becomes challenging when we move to our reduction half reaction. I have not just chromium, I have dichromate. So I need to start with Cr2O7, and that's going to react to form Cr3 plus. First things first, I need to double the amount of my chromium. I have to make sure that my coefficients match the subscript so that I can have equal amounts of chromium on both sides. The issue is I also now have oxygen. So what I'm going to do is I'm going to add oxygen to my products. In an acidic reaction, I can only add one form of oxygen. I can add either water or protons, so I'm going to add water. In fact, I need 7 oxygen, so I'm going to add 7 water molecules. So now I've balanced my chromium and I've balanced my oxygen. The issue is I've now introduced 14 hydrogen. So I'm going to now go ahead and add 14 hydrogen ions to my reactant side. So now I've balanced all my elements. The issue is I've not balanced my charge. I have 14 plus here and I have 2 minus here for a total of 12 plus charge on my reactant side. I have 2 3 plus for a total of 6 plus charge on my product side. These are not the same. So I need to somehow balance these out. Well, I can only add electrons. So I'm going to add 6 electrons to my reactant side. And this is now my reduction half reaction. 6 electrons plus 14 hydrogen ions plus dichromate gives 2 chromium plus 7 H2O. All right, these are my two half reactions. So now I need to sum them to find my full balance equation. Well, I need to balance my electrons, and I know 1 electron will not balance with 6. So what I'll do is I'll multiply my top by 6. I'll multiply my bottom by 1. I know that seems unnecessary, but I'm trying to be thorough in case you have something not 1 later on. And what I end up with is 6 iron, 2 plus 14 hydrogen ions, plus dichromate, Cr2O7, 2 minus, reacts to form 6 iron 3 plus 2 chromium 3 plus ions, plus 7 water. This is how we approach redox reaction in an acidic condition, where we need to start adding hydrogens and oxygens to help continue balance this out. Hopefully this helps you understand a little bit more. Before we end today, let's just remind ourselves on this last one. Iron was oxidized and is therefore the reducing agent. Chromium was reduced, and we will actually say that dichromate or chromium was the oxidizing agent here. Make sure that you are familiar with these terms and you can use them. Hope this helps and have a great